In this lesson, we're going to take a little bit of a look at radioactive decay, more of a look at fission and fusion, and then the primary use of nuclear fission that we have, which is generating electricity. So remember, in nuclear fission, a large atom breaks apart into two very much smaller atoms. So barium and krypton are considerably smaller. You'll notice their atomic their mass numbers are 141 and 92. And then we also have, so uranium-235 gets bombarded with this neutron. That neutron converts it to U-236, which fizzes into krypton and barium. This is very different than radioactive decay because we didn't start with uranium and end with something that's just a little bit smaller than uranium. We'd have ended with, if this had undergone alpha decay, thorium, this would have been 235 and 231, and then we'd have had a helium nucleus, He42. We didn't get that. Instead, we ended up with barium, 141, and krypton, 92, and all these other things down here, those extra neutrons. Those extra neutrons are really key because remember, this whole reaction started with that neutron bombarding that uranium-235 atom. Well, this is going to trigger more of these uranium-235 reactions. You'll notice we got out more neutrons than we put in, so it's going to increase and we're going to get more reactions, right? Radioactive decay, this gets slower over time. Fission reactions, they actually can speed up over time. So they release a large amount of energy, so the mass of all of the things that are produced over here does not equal the mass we started with. This is mass is less than the mass we have right here, and that mass was converted into energy. And you'll notice we have much smaller atoms than we started with. Fusion is exactly the opposite process. Instead of bombarding a nucleus with a neutron to make it break apart, we take and we smash two other small nuclei together. Now remember, a nucleus and a nucleus won't actually like each other. This is a very positive charge, this is a very positive charge, and so they are repelling. So we have to get it really, really hot. Hot makes these things move fast, and we have to put it under very high pressure. Pressure forces them together. And then, once they get close enough together, the strong nuclear force takes over and pulls those things together, making them stable. And that's where we get all of that extra energy released. So a little bit of mass is converted into energy, and we get out a bigger atom than we started with. We started with 2 hydrogen atoms, we end with 2 helium atoms. But again, the number of protons and the number of neutrons together stays the same. Now, how do we use fission to generate electricity? Well, generating electricity doesn't matter how you do it. All of it involves this. You've got to make some type of turbine spin, and really that's because in order to generate electricity you need a magnet and you need some copper wires around it, and you're going to take that magnet and you're going to turn it through those coils, and that magnet actually starts pushing the electrons around in the wire, and that's where we get electric current from this spinning magnet. So you've got to have a turbine hooked to this magnet to make the magnet spin. And there's several different ways we can do that. We've got like coal burning or natural gas or nuclear power. What they do is they take and burn something or get heat. Right down here we have a boiler that takes cool water, turns it into hot water. Hot water expands, and so that actually, usually there's 2 steps here. That expanding water, that steam, is going to catch a turbine here and start turning it, and then as it condenses back down, it'll also pass over another turbine and spin it. So this steam turbine is being forced to turn by the pressurized water coming out of it. Now, we've got this boiler down at the bottom that is turning coal into carbon dioxide and water, and those have to be released somewhere, and it's also generating heat. Down here we've got a hydroelectric dam, right? So just the gravity is actually pulling the water downhill. We capture some of that kinetic energy and use it to turn a turbine. Here's a wind turbine doing the same thing. Wind blows through and the turbine is turning a magnet through coils. So usually we do this by using water, either heating the water to steam or letting gravity pull water. Sometimes we use wind. A solar power plant, so where you're using photoelectric cells or solar panels, they work differently than this. They don't involve a turbine. We won't get into those. So wind, falling water, same thing. A nuclear fission power plant uses a different fuel, but it's still the same thing. We've got our steam generator, we've got a turbine. We've got our condensing things. So you're going to take water, heat it up, let it cool. And usually this is why there's a canal or a river or a reservoir by power plants, because we need cool water to come in, and then we've got to do something with that hot water once it's gone. And so you throw it in a holding reservoir to let it cool down, and then you dump it back in the river as it continues. You'll notice this water is completely separate from the nuclear reactor over here. So this is a closed loop where we're generating the heat, and then the water is put in this chamber, but it's not inside the nuclear reactor. The nuclear stuff is contained. So uranium-235 in our reactor undergoes fission. That releases large amounts of thermal energy. That causes the water to turn to steam, and then we can capture that thermal energy that expanded the water and makes it rise and then fall back down. We get that kinetic energy, spins our magnet through our wires, generates electricity. So we're just taking one form of energy, the nuclear energy stored in the fuel, converting it to thermal energy, kinetic energy, and then finally electrical energy. And then we get out this beautiful electricity that we plug into and use every day. Okay? So a lot of energy conversions happening. This is that picture but bigger. And so we do end up with a couple things that we have to deal with. You'll notice there's no smokestack over here. There is no carbon dioxide being kicked into the air, but this reactor has got its own set of issues. These control rods are there. If you throw the control rods further into the reaction, what they do is they absorb neutrons, and if the neutrons can't cause the next thing to react, then our reaction slows down, right? So our control rods control the rate of the reaction. But after that uranium-235 fizzes, it's still radioactive. It's just less radioactive. It's got less energy in it, and it's no longer capable of heating the water, but it's still radioactive. So we got to get rid of that. So like I mentioned, benefits: no air pollution, no carbon dioxide, no greenhouse gases, and we don't need trainloads of uranium to go by like we have trainloads of coal. Just a small amount of uranium can do this. But the issue is the drawbacks, and there's a couple of them. Primarily is this: radioactive waste. Radioactive waste takes thousands of years to decay. The half-lives of these things are very long-lived, and remember, decay takes time. So this isn't fission anymore. Now it's a decay reaction, and that takes a lot of time and it slows down. So we've got to do something with this radioactive waste, remove it from the population, remove it from the environment, store it somewhere where it's not going to cause damage, and it's got to be stored for thousands of years. The other thing that we have is the thermal pollution of water. When we heat up water, we can't just dump it back into the system because we've stripped the oxygen out of it, which if there's no oxygen in your water, we start to kill things. So we do have that, although this is true of it doesn't matter if it's burning coal or natural gas, we still have that water reservoir we got to deal with. And then this is probably the one that people are most scared of. If a reactor malfunctions, it can melt down and release radioactive particles into the area. In the United States, there's never been a breach of a nuclear power plant. We've not lost anything. There's been a couple accidents, but we've not lost radioactive material to the environment. Chernobyl, on the other hand, that spread nuclear waste all over the globe. Fusion plants. Currently there is an international effort to build a fusion plant. They're hoping to actually have first fusion in the year 2025. I think they're already 8 to 10 years into construction on it. Fusion is neat because we don't have radioactive waste when we're done. We're not really going to have the thermal pollution of water. Depends on how we capture the energy, we might, and no threat of meltdown because there's not radioactive fuel sources stored anywhere. The problem is, for nuclear fusion to occur, we need really, really high temperatures, and we make a plasma. And the only way to get those is to put a whole bunch of energy in. And so we've never got more energy out of a fusion reaction than we've put into a fusion reaction, which means we're not getting energy, we're losing energy.